So now I am sharing the entire screen. Give me some moment. Now it is okay, I think.
Yes, sir. You just change. Yeah, it's coming.
Okay. So now I think that we can start.
Okay. So, good evening to one and all. We have now 72 participants, and few more will be joining in. So, we have our expert speaker for the session. He is Dr. Anirban Karmakar. So, before we start, I am introducing the speaker, who is also the coordinator of this program. Myself, Shanivar Mujumdar, I am the co-coordinator with Dr. Anirban Karmakar for this program. So Dr. Karmakar has completed his PhD in engineering from Jadavpur University, Kolkata, India in 2015. He has more than 17 years of teaching experience and currently is holding the post of assistant professor in Department of Electronics and Communication Engineering at Tripura University, which is a central university. He has around 50 research articles in refereed journals and many more in international conference proceedings. He has served as reviewer in different international journals and has been awarded the best paper, he or his students, a lot of times in different international conference. He is a senior member of IEEE and has organized different workshops in capacity as convener and completed various funded projects by various organizations like UGC and many more. Currently, 4 PhD scholars are pursuing their PhD under his guidance. He has already awarded a few of his candidates. His area of research includes planar and fractal wideband antennas, arrays, circular polarized antennas, DRAs, etc. And he is an expert of this subject, which he is organizing the uh, this Atal FDP on. So if you have, he has been handling the sessions, you have been a part of it, you have seen him handle the session with ease, and he has eased a lot of load from my side, and he has taken the load himself. So thank you, sir, for being here and for this expert session.
Thank
I
you.
hope it is over to you.
Okay. So thank you, Professor Shanibar Mujumdar, for your nice introduction. So now here I am starting my presentation on a fractal-based single-band dielectric rectenna for RF energy harvesting. Basically, this is my contents. At first, there will be the brief introduction of RF energy harvesting, then the birth of dielectric resonator antenna, design requirements, applications of dielectric resonator antenna, advantages of DRA as compared to patch antennas, fractals and introduction, Hilbert curve, configuration of proposed antenna design, step-by-step procedure of the proposed antenna, simulated performance of the proposed antenna, fabricated prototype simulated and measured results, proposed rectifier circuit configuration, parametric study of the rectifier circuit, simulated and measured results, simulated performance of the rectifier, experimental validation of the rectenna systems, conclusion, and the references. So now, what is uh, RF energy harvesting? Actually, in short, RF energy harvesting is nothing but that the system that converts RF signal energy into the DC power. Wireless energy harvesting technology can be used by receivers to harvest some energy from the RF signals. So this energy can then be used to power devices or charge batteries, making it ideal for low power sensor networks, IoTs, RFID, and a range of other applications. So in this figure, we can see this is a simple transmitting antenna, and this is the simple RF generator, which is generating a scattered RF for the automatic wave in our environment. And this scattered RF is being received by the receiving antenna. Then this After receiving the scattered RF, the corresponding current will be fed to the impedance matching network. Then it will be fed to the rectifier or voltage multiplier, then the power management circuit, and after that we will get the actual DC source, which will be available for many low power sensor networks, IoTs, RFID, and a range of other applications. So as this RF energy harvesting circuit is associated with a dielectric resonator antenna, here I will introduce that DRS, that is called the dielectric resonator antenna. So in dielectric resonator antennas, the most essential part which is being added by the DR, that is the dielectric resonator. So this is some samples of the dielectric resonators over here, and this is a sample picture of the dielectric resonator on which a simple DR has been placed. And as a whole, this antenna will be called as dielectric resonator antenna. So what is DR or dielectric resonator? It is a simple piece of dielectric material. So a study of dielectric resonator antenna has been carried out by S.A. Long and Shen in 1980s. Dielectric resonator basically consists of dielectric material having very high permittivity. This dielectric resonator can behave as an antenna whenever it is properly placed on a substrate and fed by a simple microstrip or probe-feed line. Some design requirements are there for any kind of dielectric resonator antennas. So in the pictorial diagram, we have shown different kind of dielectric resonator antennas of different shapes which are being placed on the dielectric substrate FR4 or many others. So over the years, a wide range of dielectric resonator antennas have been designed due to their distinguished properties like simplicity in structure. You can see the dielectric resonators are mostly simple in structure and their fabrication are much simple. They are low profile, they are lightweight, and after all, after using these dielectric resonator antennas, we will get much enhanced bandwidth in antennas. Now, some applications of dielectric resonator antennas can be discussed. The DRS can be used in 5G applications, for communications or GPS antennas, and as well as for ultra-wideband antennas, which provides the range of 3.1 to 10.6 gigahertz. Now, why we will use the dielectric resonator antennas instead of a patch antenna, which are being popular for past few decades? Now, this is a simple patch antenna, and this is a simple dielectric resonator antenna. So, DRA can achieve wide impedance bandwidth as compared to other patch antennas. DRS has high radiation efficiency. DRS has high degree of flexibility and versatility, and it has higher power handling capability. The work we have done on RF energy harvesting, it is associated with a dielectric resonator antennas as well as fractal shape. So here I am introducing the fractal. So what is fractal? It is nothing but it came from the inspiration for the development of fractal geometry, which came largely for an in-depth study of pattern from the nature. Fractal have been successfully used to model such complex natural objects like cloud, galaxies, mountain ranges, coastlines, trees, leaves, palms, and much more. Mandelbrot coined the term fractal about 20 years back in his book named The Fractal Geometry in Nature. He proposed the fractals and fractal geometry could be used to describe real objects such as trees, lightning, river, meanders, coastline, and so forth. Following figure shows some natural fractals available in nature, such as trees, coastline, as lightning is. So we have just omitted this such kind of figures in our slides. So only one figure has been added, which is a natural example which is available in nature, which is called the fractal. So this is the same similarity of nature in fractal. We can see all patterns are much self similar to each other, which we can call as a fractal shape. Hilbert curve is one of the popular shape in the fractal. Here we are discussing a little bit about the Hilbert curve because we have used this structure in our antenna design, which is being used in the RF energy harvesting technique. The Hilbert curve is a continuous fractal space-filling curve first described by German mathematician David Hilbert in 1891 as a variant of the space-filling piano curve discovered by Piano in 1890. So here we can see the different generations or iterations of the Hilbert curve. This is the first iteration, this is the second iteration, this is the third iteration of the Hilbert curve. So now here we are discussing the configuration of our proposed antenna. So this is the isometric view of the proposed antenna, which we have used in our RF energy harvesting technique. And this is the top view of the antenna. So in this isometric view, you can see a top-loaded DR, a top-loaded cylindrical DR is there. And at the bottom of the DR, or the DR is placed above a FR4 substrate, and the DR is excited through a aperture coupling. You can see the aperture over here, and on the aperture, a fractal Hilbert shape strip has been placed. So this is the isometric view of the antenna, and this is the top view of our antenna. So in the top view, easily visible that this is the FR4 substrate, and on the FR4 substrate there is a simple aperture has been cut, and just below the aperture or just below the substrate, a simple microstrip line is there to excite the DR, and above the microstrip line, a Hilbert fractal shape is placed to tune the antenna at the proposed resonant frequency, which we will discuss later on. So it comprises a cylindrical DR and with alumina, that is Al2A3. This DR material is made up of Al2A3, which is much cheaper material with a dielectric constant of 9.8 and a loss tangent of 0.002. The chosen DR is placed on an FR4 substrate with a substrate dimension of 120 into 120 into 1.6 millimeter cube and a dielectric constant of 4.4. The diameter and height of the proposed DR material are 76 mm and 28 mm. The Hilbert shaped fractal strip, a Hilbert shaped fractal strip here we can see also, is introduced or incorporated into the circular aperture to fine tune the antenna at the 2.4 GHz resonant frequency Wimax band. The antenna assembly is excited by an I-shaped microstrip line that is coupled to the circular aperture, which in turn excites the cylindrical dielectric resonator antenna. So this microstrip line excites coupled to the circular aperture and excites this dielectric resonator antenna, which in turn results in radiation, or you can say it results in efficient radiation. So here is some step-by-step design procedure we have shown. This is the different design steps of our antenna, starting from antenna 1, antenna 2, and antenna 3. DRA is excited through a circular multiple resonances are of
Sir, screen is not visible, sir.
tune the antenna to
Sir, screen is not visible, sir.
Okay, let me check.
Sir,
Not
visible, sir, now.
okay. Okay.
કામ પતી ગયું કે ચાલે છે?
Okay. So now to fine tune the antenna at 2.4 gigahertz, we have gone up to
ના ના ખાલી એક જ ટાવર છે.
okay. So now, so to fine tune the antenna at 2.4 gigahertz, we have introduced the Hilbert curve of second iteration, which will fine tune the antenna at 2.4 gigahertz. But before introduction of the second iteration of the Hilbert curve, we can see multiple resonances are being observed. So this is the simulated performance of
આપણે
the
આનું કઈ રીતે
proposed antenna.
આમાં ગાડી સાથે
Just a minute.
સ્પંજ સાથે સ્પંજ અને કાપડ હા પ્રત્યે તો રેડી છે. 3000 હે
કારીગરનું પણ સોફામાં તો મારું બાકી 2500 નું પણ ચાલે છે ક્વોલિટી
એનું ખાલી મટીરિયલ લેવું હોય તો મળી જાય ને આપણે
So,
કાપડ અહીંથી
actually, all the participants are requested to mute their microphone, please.
તો આ જે છે આપણે આના કેટલા જે આ મેં સિલેક્ટ કર્યું હોય ખાલી રાખો.
So, am I audible now? Okay. So, so here we have shown the simulated E-field vector distribution inside the cylindrical dielectric resonator antennas at 2.4 gigahertz at different planes. So where we have shown only the 2.4 gigahertz because this is the targeted frequency. This is the targeted frequency of our energy harvesting. We want to harvest the ambient energy or which is readily available in terms of RF at 2.4 gigahertz. So here the simulated electric field vector distribution inside the cylindrical dielectric resonator antennas has been shown. Actually the movement of the electric field arrows confirm that the antenna operates in the T02 del mode at 2.4 gigahertz. The TMNP mode notation, where M, N, and P present the half cycle sinusoidal variations along the azimuthal, radial, and axial axis, respectively, which is being used to describe the field orientation. The symbol del indicates that the field variation lies between 0 and 1. Here, the surface current distribution at different frequencies 1.9 GHz and 2.4 GHz has been shown. So the 2.4 GHz is our intended frequency, but here additionally we have shown the current distribution at 1.9 GHz to show the superiority of the 2.4 GHz. So at 1.9 GHz, we can see the current becomes more localized with higher concentration in specific regions. And which is due to the excitation of higher order resonances. So as the fractal geometry increases the structural complexity, the current at 2.4 GHz becomes more concentrated along the strips, enhancing energy coupling into the resonance structure and improving impedance matching. The current distribution indicates that the proposed antenna operates efficiently within the single frequency band of 2.4 gigahertz. So here, fabricated prototype and simulated and measured results of the designed antenna. So all the prototypes of the antenna was developed to validate its performance. The structure was simulated using the commercially automatic simulation software CST Micro Studio. The S11 and the gain performance of the prototype antenna was measured using an Agilent PNA LN5230 network analyzer and compared with the simulated result. The gain was measured in the broadside direction with a maximum value of 6.5 dBi, which we have got at 2.4 gigahertz. The antenna achieves a maximum radiation efficiency of 89.2%, which means that the antenna effectively radiates or receives most of the input power for harvesting. So here is the proposed rectifier circuit configuration. So why rectifier is required in energy harvesting technique? Actually, a rectifier is an essential component in the rectangular system which is responsible for converting ambient RF energy into the usable DC electrical power. The rectifier circuit includes an impedance matching network, a diode, a DC bus filter, and a load resistor. The impedance matching network ensures matching between the receiving antenna and the conversion circuit at the desired operating frequency. It maximizes the power received and delivered to the rectifier circuit for conversion. The diode is a critical element of the rectifier circuit, and the performance of the rectifier largely depends on the diode selected. Therefore, choosing the suitable diode for optimal rectifier design is essential. Basically, Schottky diodes are ideal for rectifier design due to their low turn-on voltage and high switching speed, and they are found appropriate at radio frequencies. A DC bus filter is usually connected after the diode to smoothen the signal. So here we have done some kind of parametric study of the rectifier circuit. So it has been performed to improve the rectifier circuit's power conversion efficiency. In short, that is written PC and the output voltage V out. The performance results regarding S11 and frequency for defined input power levels for 1 kilo ohm load resistance have been shown. The proposed rectifier operates efficiently at the resonant frequency of 2.4 gigahertz over a wide input power range from minus 5 dBm to plus 5 dBm. So here we can see whenever we are varying the input power from minus 5 dBm to plus 5 dBm, we can see there is almost stable resonance we are getting from the antenna system. Here both simulated and measured results have been shown. So here we have shown the power conversion efficiency and voltage output of our circuit of the rectangle. The performance variation of the proposed rectifier for the PC and V out in figure A with and without matching network, and in figure B simulated and measured results. So the impact of the impedance matching network on the rectifier power conversion efficiency and DC output voltage has been shown. The rectifier demonstrates improved matching performance across the frequency band for various input power levels. Here, this is the various input power levels has been plotted in the x-axis. The measured and simulated results of PC and V out as a function of P in has been displayed. The proposed rectifier circuit achieves a maximum PC of 66% at 5 dBm input power. The designed rectifier offered a PC of 56% at 0 dBm, and a maximum PC of 66% is possible at a P-in value of 5 dBm. The Vout is 0.78 volt at 0 dBm and 1.44 volt at 5 dBm. The simulated and measured results of PC and Vout are presented. So if we closely analyze these two plots, we can see this is the results of PC with matching network and without matching network. So we can see that the without matching network, the performance of the PC is too poor, but with matching network, we are getting an appreciable performance of the power conversion efficiency. And this is also the plot of Vout with and without matching network. So we can see, we can get that we are getting much better response of the Vout with matching network only. So this is again the simulated and measured plots of PC and Vout. We can see the both simulated and measured counterparts are tallying with each other in a very good manner. So here we have shown the simulated performance of the rectifier. So here different values of load resistance has been taken, starting from 0.8 kilo ohm, 1 kilo ohm, 1.2 kilo ohm, and 1.4 kilo ohm. So this plot is plotted for PC versus P in dBm. P is the input power. So we can see whenever we are changing the load resistance, there is a little variation in the PC plot. Means the PC will be much stable if the load resistance has been changed. Here also the plot of the P in for different load resistance value. The load resistances have been changes from 0.8 kilo ohm to 1 kilo ohm, 1.2 kilo ohm up to 1.4 kilo ohm. But also here we can see the stability of the P in, which indicates the stability of the PC as well as for Vout for different values of P in and RL. So at different values of RL, we'll get the stable response for PC as well as for the Vout. So we can conclude the slide by saying that the PC and the output voltages are studied for different values of load resistors and the corresponding outcomes are displayed. The rectifiers offers good impedance matching with a load resistance value of 1 kilo ohm. Thus, the maximum of the received power is transported to the rectifier circuit. This increases the PC of the output voltage of the proposed rectifier circuit, which are higher than all other load values. So here we have shown the experimental validation of the rectenna system. Here is the experimental setup of the antenna, and here is the fabricated prototype of the DR rectenna. So this is here we have shown the total DR rectenna. Here the dielectric resonator antenna, above the FR4 substrate, the DR has been placed, and this is the fabricated rectenna circuit. You can see, and this is the experimental setup of the rectenna. This is the transmitting unit consists of horn antenna, RF generator, and these are receiving unit consists of receiving antenna, consists of receiving antenna and rectenna circuit at 2.4 gigahertz, multimeter, and all. So a wireless power transfer system usually using microwave technology consists of a transmitting unit with an RF generator and a horn antenna to transmit the RF signals at 2.4 gigahertz and a receiving unit with a receiving antenna, and antenna circuit converts RF energy into the DC power. The converted power is measured by a multimeter, demonstrating the system's ability to transfer and harvest energy wirelessly. The antenna and rectifier components were developed as prototypes and connected using an SMA connector. The rectangular system was initially designed to harvest RF energy from the ambient environment. The rectangular system is positioned at a maximum distance of 200 centimeters from the transmitting antenna, where the energy density is approximately 0 dBm. The antenna achieves a peak power conversion efficiency of 64.4% at the input power of 5.5 dBm. The rectangle's output voltage Vout measured using a voltmeter, that is 0.7 volt at a P of 0 dBm and 1.34 volt at P of 5.5 dBm. So, as an output, we are getting the output voltage of 0.7 volt with P or the P input power of 0 dBm and 1.34 volt with P input power of 5.5 dBm. So this is the references or references we have referred in our paper. And thank you. Okay, so now I will request all the participants. They can raise any questions if you have.
Excuse me, sir. Am I audible?
Yeah, you're audible.
Sir,
Okay, sir. You have used the Hilbert fractal. So, if I choose the Koch fractal or Sierra-Smith fractal or something else, then have you compared, sir, with other type of fractals?
Yeah. Actually, the thing is that here our focus was only to get the desired resonance frequency at 2.4 gigahertz. That is a Wi-Fi band, okay? So initially, we have seen that we are easily getting the desired resonance frequency at 2.4 gigahertz by a Hilbert curve. So there was no issue of considering other Hilbert structures over here. In our internet frequency, we have already achieved, so our factors were not tried.
Okay, sir. One more question. You have taken the iteration 1, that means the order of the fractal geometry, probably you have taken the iteration number 1. So if I continue that to iteration 2, the size of your design may be reduced further.
No, actually, this is a valid question, but the thing is that just if we go through the further iterations, that is iteration 2 and 3, it may happen that we will get the loss in the resonance frequency in much good manner, but it will complicate the design procedure. So as we have desired our return loss just in the range of -20 to -30 dB, I think that it was sufficient for energy harvesting technique. So also here you have a valid question. This can be tried with other factors also, and with further iterations can be done.
Okay, sir. One thing I want to add, for if I increase the iteration order, then due to some more number of cross couplings will be there due to more bending, and this will give some more capacitive and inductive effect to the system. And you are correct that complexity will be increased and due to additional cross coupling.
Yeah.
And it may hamper the overall performance of the system.
Yeah. Actually, that factor techniques are being used in antennas from last few decades. So it is not true that each and every time the factor will add some good benefit to our antennas, in my opinion.
You are correct, sir. My research area is filter, and I have designed lot of design in by fractals. But my opinion is also correct that fractals are all the time are not good. There may be some other structures.
Yeah, and also that if you go through further higher amount of iterations, and there is few industries are available in India who can fabricate those higher factor iterations in perfect manner.
Yes,
Is
sir.
the main thing.
Yes.
So in India, in antenna research or any type of research in India, we have seen some problem we have faced mostly regarding the fabrication.
Yeah. Sir, I
Mostly
hope you have
regarding the fabrication.
yeah. I hope you have heard about Atlantic Circuits of Hyderabad. I have contacted them regarding one design of fractal, and they strictly denied that it is not possible for them to calculate
Yeah.
due to the complex
So,
structure.
yeah. So this is the thing. This is the thing we have to take care about. Thank you, sir. Thank you for the question. So if you have, sir, any other questions, you can go ahead.
Good evening, sir. Good evening,
Yeah.
sir. Sir, thank you for the very informative session. Actually, I have a question. You have mentioned a rectangle.
Yeah.
So, can we simulate that type of antenna in CST?
Actually, the thing is that, madam, here
Yes.
in the rectangular system consists of two parts, a rectifier and an antenna. Here the antenna part is being simulated and designed using CST. But
Yes.
the rectifier part is totally designed in ADS, that is the advanced design system software. To define software, you need to know and you need to simulate efficiently to get an rectangle.
Okay. Thank you, sir.
Any other questions?
Audience, if you have some questions for Dr. Karmakar. So I hope you have gained a lot from his session. He will be having another session tomorrow. So thank you, sir, for being here.
Thank you.
So can we call it a day?